Lesson 5.1, we are going to solve systems of equations by graphing. Our learning goal today is that you can solve a system of equations by graphing, but not only can you do that, but you're going to make sure that whatever happened on the graph will check out in both equations of the system. It has to make the equations true, otherwise you didn't really accomplish getting to the right solution. So two equations, so we're going to work with two equations at a time, with two variables, we're going to have an x and a y, are called a system of equations. Fill in the blank. System of equations. Setting up a system of equations, when you have two or more things to solve for, is the most efficient way, actually, to problem solve. Well, I'm not going to make you have to solve for three unknowns. We're just going to work with two. Three gets a little tricky. We'll just work with two unknowns, like our problems you did, the first problem that you did for today. You did not know how many chickens there were. You did not know how many llamas there were. You were solving for two unknowns. To estimate, because in reality, when we are graphing, the picture shows us a solution, and I always give you nice solution ones, by the way. You don't always get when you're solving, you don't always get integers. You don't get those numbers all the time, like, oh, x equals 4 and y equals -2. Sometimes it turns out that x equals 3 1/3 and y equals a -1/2. Well, would that be easy to tell from a graph where that ordered pair is, where those lines are crossing? It would not be quite as clear to you where the point of intersection is. So what would happen is you would probably estimate integers. And then, when we go to make sure that they make the equations true, we would find out, oh, they don't. So we call finding the solution from the graph estimating it until we really actually check it out algebraically and make sure it makes the equations true. So we are going to, when we're going to estimate the solution, when we are going to find the solution to a system of equations using a graph, we're going to determine the point of intersection. We're going to see where do these two lines, because we're going to have two equations, thus we're going to have two lines. Where are those two lines intersecting, and where they are, we're going to write down an ordered pair. And we know that the ordered pair has an x value as its first coordinate and a y value as its second coordinate. Some of this starting to come back to you? Some of you, yeah, some of you are still fuzzy. Okay, y equals 3x plus 1, y equals -x plus 5. That's our system of equations. We have two equations with two variables. They both have x's, they both have y's. They don't both have to have the x's and y's, but at least one of them does. If they both have x's and y's, cool. If only one of them does, cool. We still can use this method to solve. So, anybody remember what that form is called for that linear equation? Y equals 3x plus 1. And by the way, the other one's a linear equation also. Y equals -x plus 5. It is a linear function. What type of form is it in? Well, standard form is this. Ax plus by equals c. Do they appear to be in that form? The x's and the y's being added together on the same side and a constant on the other side? So are these in standard form? No. No? Standard notation. Well, not really, because it's kind of really the same thing. If there is such a thing really as standard notation for linear functions, I'm not really sure what that is. So we're kind of really still talking about standard form. Julia? Y equals mx plus b form. Oh, she's got that much. Y equals mx plus b. Anybody remember what the m represents in that equation? Slope. And what does the b represent? Y-intercept. So Cody, we need slope-intercept form. Slope-intercept form. When the equation is solved for y, when the y is by itself, it's a 1y, a positive 1y. Then we say it's in slope-intercept form, and it's graphing friendly. It's ready to pull the information out of it that we need to graph it to help us solve this system. So let's graph the first one, y equals 3x plus 1. What's our m value? What's our slope?
3.
Noah?
1.
The 1 is our slope? Y equals, okay, let's do this. Y equals mx plus b.
Oh,
3. Yeah. 3 is our slope in this one. Now, do you remember when we use the slope of 3, what are the two different ways we can go about that? What are the two different ways we can go about graphing a slope of 3? One of them, Cody.
Is it positive or negative? If it's positive, it is up into the right.
Okay, so let's do that. Let's say that this then means we can go 3 up and 1 to the right, because can't we make 3 over 1? Remember, slope is rise over run. So when it's an integer value, we need to make it into a fraction so that we have a rise over run. Well, the only way we can legally make an integer into a fraction is by putting it over 1. Because anything divided by 1 is itself. So 3 divided by 1 is still 3. We have not changed its value. So we can go up 3 and right 1, or we can do what? What's another way we can still accomplish a slope of positive 3? Clara? Down 3 and left 1. And you can put your arrows first if that makes more sense to you. Whatever. So we have two different ways to use this slope. Well, we can't use the slope until we have a starting point. And that starting point is our b value, our y-intercept. What's our y-intercept? 1. Our y-intercept is 1. So in other words, we're going to start at 1 on which axis?
X-axis.
Y-axis. The y-axis. We want to start on the y-intercept. We want this to be, so we're going to start at 1. So we're going to put a point on the y-axis at positive 1. And from there, we're now going to make 2 more points. Remember, it was always a minimum of 3 if the graph would hold 3. I suggest on these, sometimes you make as many points as you can to get better lines, which will then give you a clearer picture of where the point of intersection is. Okay? So let's use both of them. Let's do the up 3, 1, 2, 3, up from that point and over 1. Or we can go back to it and we can say, I could use the down 3 and the left 1 and make a point. Because even if my, that first point that I made after the y-intercept, if I go down and left 1, I'm on the y-intercept, aren't I? Go down 3 again and left 1. I could really just keep doing this until I run out of some grid lines. I've run out of grid lines going, I can't go anymore. Take your ruler now and draw that line. Do not move on to the other equation until you draw the line for this one. Sometimes those points are so close to each other from the 2 lines combined, and you're like, I don't know what goes with what. Grab one line at a time. Okay. Questions on that one? Anything we should talk about? It's still unclear. Okay, you get the next one ready to graph. See if you can. What's the m value? Did you go ahead and do it on your paper? What's the m value? What's the b value? Take that m value and state what are the 2 different ways you think you could do it so that you get a good slope, because we're also going to remind ourselves of what kind of behavior the line should have according to its slope. What is the m value for this one? What is the slope of this one? Noah? Negative 1. Okay, Noah, why don't you share with us one of the ways we can use this slope?
Down 1, right 1.
Okay, so we use the negative up going down, so we have to head in the positive direction for the other one. Or we have another option. What if I want to go up? Can I go up?
Yeah.
Okay, then I would go up, class, up 1, and now I got to use my negative up going left. So I'm going to go 1 up, and I can go 1 to the left to make sure that I use my Notice in the other one, when we were going down 3 and left 1, we were going negative, negative. Is a negative divided by a negative a positive? Do you remember that from last year? Is a negative divided by a negative a positive?
Yes.
Yes. And didn't we have a positive slope in the first one? A positive 3? Yes. And remember, when there's a positive slope, what should be the behavior of the line? Should be rising from left to right, and that's what we got, didn't we? Okay, so now when we graph this one and it has a negative slope, what should its behavior be? It should be falling from left to right, shouldn't it? Instead of rising from left to right, this one better be falling from left to right. Where is it starting with? Where are we going to start on this one? 5. Okay, the B is 5. So we're going to go to 5. Okay, can we go down 1 and right 1? Sure we can. In fact, we land right on that other one's line. Can we go up 1 and left 1? Not really, because unless we want to draw some more grid lines, right? Do you want to do that? No. Can we keep using the same 1? Because between any 2 points, it has the same slope. So we can keep using the first one where it says go down 1, over 1, down 1. I'm just going to go crazy till I run out of room, and then I'm going to graph my line. And if the 2 lines intersect in 1 point, we say it has how many solutions? 1 solution. And that solution is an ordered pair. What do we estimate the ordered pair solution is? 1, 4. Okay, so we're going to estimate that our ordered pair solution is 1, 4. We're talking about that point right there where it's intersecting. Ordered pair 1, 4. And now we're going to check it. How do we check it? Well, we don't use the graph anymore. We use what, Noah? Yeah, we need to use the equations, right? We have to check it in both of them. So we're going to write down both equations. Y equals 3x plus 1. And we have to check it out in y equals negative x plus 5. It has to make both equations true. So we're going to put 4 in for y, because that's what we say y is from our ordered pair. Remember, y is 4, so we put 4 in for y in both of them. And in for x, what are we going to put? 1, because our x value is 1, so we put 1 in for x. Notice what happened. That negative sign that's in front of the x in the other one, it's still there, isn't it? It's out front of the x. It says, you know what? I'm here, and then there's the x. So we still have it there, and then we substitute the 1 in, and now we finish bringing down the plus 1 in this one, and this one I bring down the plus 5. It's called our substitution step, right? We're subbing in what we think the solution is. We need to make sure it makes the equation true. So 4 is 4, can't do anything with that. 3 times 1 is 3. 1 is 1, so it's plus 1. Might as well, I'm going to finish up over here. 4 is 4 equals 3 plus 1 is 4. It checks out in this one, it makes it true. 4 does equal 4, doesn't it? That's a true statement. Okay, how about over here? Bring the 4 down. That negative sign out in front of that 1, what does it do to it? Changes it to a negative 1. Do you remember last year how I said to you the negative sign can be replaced with these words? The opposite of. Remember that? So when you see a negative sign, you can also use these words, the opposite of. So we're really asking for what is the opposite of 1? Negative 1. You know that number that's on the other side of 0 that has the same distance from 0 is its opposite. So 4 is 4. What is negative 1 plus 5? 4. Because we want it to be, or because it really is? Because it really is, yeah. Okay, checks out in both of them? So to have good notes, we're going to say the solution actually is, we said the estimated solution is, we checked it out. We're going to say the solution is. So in other words, our final answer will be an ordered pair. A It's like our final answer. Here's what we believe the solution is. What do you think? Are there any others that would make both equations true? Are there any other points, any other ordered pairs that would make both equations true? How about this point right here? How about this one? Ordered pair 5, 0. Would it make one of the equations true, or none of them true, or both of them true? None of them? Isn't it on one of the lines? Shouldn't it make that equation true?
Can I get Juan Gill and Jonathan Langer to the junior high office, please? Thank you.
On that line, it better make that equation true. So that's the line that's falling from left to right, so that must be this equation. If I put 5 in for x and 0 in for y, let's see if it makes it true. The opposite of 5 is negative 5. Negative 5 plus 5 is 0. And that's the y value for, it makes that equation true, doesn't it? It better. It came from that line. Does it make this equation true? Let's try. 3 times 5 is?
15.
15. 15 plus 1 is? 16. The y value better be 16 then. Is it? No. So, you know what? Here's the reason I'm making this point right now. Here's what students want to do. They want to check out one of the equations. And if it makes that equation true, awesome, I can move on now. Is that what you can do in a system of equations? You have to check it out as both of them. It has to make both of them true. Because it might make one of them true, but it can't make both of them true or if it's not the point of intersection. And like the one I circled is not the point of intersection. So in this case, because we do have one point of intersection, we should only come up with one ordered pair answer. It can only be in one order. It's the only solution to this. Okay. Any questions? Just come back to you now. You can get out a sheet of loose leaf paper. That's what you're going to show your